Righto, Level 2 Physics. We're out here today to learn about free body diagrams, and we're going to incorporate into this a little reminder about Newton's laws as well, but I hope you've got those all on lockdown from previous learning. So free body diagrams, they're diagrams where we separate out just one body, just one object, and we draw the forces onto it. A force. What's a force? A force is a push. If we push something, that's a force, and it's measured in newtons. So, in the most simple form, if we think about you standing there, not moving, the forces that are acting on you are gravity pushing you down, and so long as you're standing on something, you've got the normal force, that's normal, meaning at right angles to the surface you're standing on, that normal force pushing up. Those forces are equal and opposite. That means that the net force is zero. If you added those two forces, nose to tail, they would join up perfectly, and so the resultant force, the resultant vector, would be zero. That means that acceleration is zero, and that means your speed is constant. Newton's first law. A body at rest will stay at rest, and a body in motion will stay in motion at constant velocity so long as no net force acts. Newton's first law. That's an example. And that's the simplest way we can write Newton's first law. When the sum of the forces equals zero, the speed is constant. Now, the second point that we could look at is what happens if we took the ground away. What would happen if we removed the normal force? Suddenly now, we've only got one force. The net force is now mass times gravity. The acceleration is now negative 9.8 meters per second squared. That's the value you're going to use this year. And the speed is not constant. We're going to go into a lot more detail about exactly what the speed is, but at the moment it's enough to say that it's not constant. And so in this case, the net force is that force there. There are no other forces acting. Newton's second law, then. Newton's second law, I've boxed it up in red because it is on your formula sheet. The net force is equal to the mass times the acceleration. Mass in kilograms and acceleration in meters per second squared. That's Newton's second law. Newton's third law. We're going to zoom out a bit to have a look at Newton's third law. So, for Newton's third law, we've zoomed out a little bit to consider our falling physicist and the Earth. And we can in fact see that while our falling physicist experiences a downward force due to gravity, the Earth experiences an equal and opposite force, which is also due to gravity. Now that's Newton's third law in action. For every action force, there must be an equal and opposite reaction force. And a key point is that those two forces have to act on different bodies. So just as hard as the Earth is pulling us down, we're pulling it up with exactly the same force. Why don't we notice it moving? Just think how massive it is. Same force, same F, much greater mass, and so much, much smaller A. Now we're going to try and extend this a little bit more. So now we're going to have a go at thinking about what this might look like if we bring this up to a more complicated level and start thinking about objects on slopes. What about if we park our car on a slope? Handbrake's on, so that car's not moving. Not moving, Newton's first law. What does that mean about the total force? Total force is 0. It's not moving, therefore the net force must be 0. I want you to have a go at drawing on the forces that are acting on this car. Clue, there are 3 forces acting on this car. Pause the video, have a go at drawing them on. Do it now. So hopefully you got 3 forces, something like that. I'm sure that everyone worked out that gravity goes downwards. We have to be careful with our normal force now that we're on a slope. Normal means at right angles to. So at right angles to the slope, it's pointing up at an angle. And then the third force that I hope you all got was the force due to the brake. Now that's what stops the car from rolling down the hill, and that acts parallel to the slope. So some key geometry points for you there. Perpendicular to the slope, parallel to the slope. Now what I want you to do, what we are going to do, is take those 3 forces, and we know that the car is stopped, we know that the net force is 0, so I want you to draw those 3 forces together so that they form a closed triangle. And it's going to be a right-angled triangle because the brake force and the normal force are at right angles to each other. So once again, pause the video, have a go at drawing the triangle before I do it for you. Hopefully you got something like that. We got the gravitational force directed downwards. That one there, that's the normal. And that one at the top's the brake force. And so those of you who are familiar with trigonometry, you can hopefully spot that we can work out the size of the normal force by using mg cos theta, and we can work out the size of the brake force, the opposite side, by doing mg sine theta. And you can probably persuade yourselves that that 15 degrees there is the same as that one there. And now finally, we're going to examine just exactly what happens if you forget to leave the handbrake on when you park your car on a slope. There's still gravity, and there's still a normal force, and it's still perpendicular to the slope. But the best way of going about this problem is to just think about gravity. And what we're going to do is we're going to split that gravity into 2 components. We're going to split it into a component which is directed down the ramp that can cause acceleration, and a component that's not directed down the ramp that cannot cause acceleration. Remember that any vector you can split into 2 other vectors at right angles to each other. Now normally we choose X and Y, but in this case we're going to choose down the ramp and into the ramp. Now those eagle-eyed physicists amongst you will have noticed that this is exactly the same size of triangle, the same dimensions as the previous triangle, because we've still got mg, gravity, on the hypotenuse, and the force directed into the ramp, the component of gravity directed into the ramp, in fact, is going to be equal and opposite to the normal force, whilst the component directed down the ramp is going to be equal. That's what's going to cause acceleration. That there is the unbalanced piece of the force. That's what's going to cause the acceleration. And that one there, remember from last time, it's going to be the mg. It's the opposite side of the triangle to the angle, so mg sine theta. Now the other way of thinking about this, of course, is to add the two vectors together that act on the car and find out what the resultant is. Thinking about it that way, we've got gravity directed downwards, normal force directed at right angles to the ramp, and therefore the resultant force is going to be that one there. And you can see that once again we've managed to draw the same triangle. We could work out that side there, and we're going to get exactly that same mg sine theta that we got on the other one. So that's how you work out the size of the forces acting on a body on a slope.